Okay, hello to everybody. Let's start. So today we'll discuss another one example of Markov chain, which is a rather famous example. This is Galton-Watson-Birst-Death model. Basically, there are many different Birst-Death models, but this is, I think this was the first one and possibly the simplest one. So Francis Galton, at the middle of the 19th century, maybe not in the middle, maybe in the second half, he was interested in the following question. So it was known that in Britain the noble families, just the family names of nobles started to disappear. And he tried to understand what is going on, and he created the following model. And basically, he found that this model does not well describe the situation, but it turns out that this model well describes another, like more serious situations. For example, the behavior of chromosomes and so on and so forth. So the model is as follows. Let us consider random variable xi0. Then we will also have, of course, random variable xi1, xi2, and so on. And as you understand, they will form a Markov process. So xi0, this is a number. So just more generally, xi k, this is a number of individuals in the case generation. What does it mean? So at the initial moment of time, we have xi0 individuals. So let me draw a picture. For example, xi0 almost surely equals to 3. Okay, just for an example. Then each individual gives birth to a random number of descendants. For example, this one, this is the first, this is the second, this is the third. This one gives birth to, for example, to 3 individuals. This one gives birth to 0 individuals, and this one gives birth to 1 individual. So just and these guys, they die. So in the second generation, you have now at the picture 4 individuals, but well, I will call it the first generation because I will start from the 0th generation, okay, as usual in Markov chains, and so on and so on, and then you are interested in the behavior of this random process. More rigorously, we have the following situation. Each individual gives birth to eta ni individuals. So this is eta ni. This is a number of descendants of individual number I of the nth generation. For example, in my picture, eta 0, 1, this is a number of descendants of this guy, so it equals to 3. Then eta 0, 2 equals to 0, and eta 0, 3 equals to 1. For example, if this guy gives birth to another 2 individuals, and this guy gives birth to only 1 individual, and this give nothing, then this will be the first, this will be the second, this will be the third. In this case, psi2 equals to 2, and eta, look, this one, this is 1, 2, this is the third, right? So eta 1, 3 equals to 1, eta, and this is the fourth, eta 1, 4 equals to 2, and for the other j, eta 1j equals to 0. Okay, so is the model is clear?
Yes.
Okay.
Sorry, can I ask? We in the definition of eta, we define the subscript to be the number of the generation. Why
Yes.
do we have eta 0?
Why do we have eta 0? Yeah, because it's, I mean, because the I start with the zeros generation.
Yes, and then in the first generation, there will be 3 descendants of
Yeah,
individual 1, according to this notation.
In the first, okay, thank you. Wait, number of descendants of individual. No, I think that everything is okay because just I define eta as a number of descendants of individual
with number I in the nth generation. Okay.
Yes. So what do we assume about the random variables eta? We assume that eta and I are independent, identically distributed, identically distributed, and also they're independent from psi 0. Okay, so the initial condition is independent from these numbers of descendants. And then according to this model, we have the following formula: psi n plus 1, so the number of individuals in the generation n plus 1 equals to psi n 1 plus etc. plus eta n 2 plus etc. plus eta n, and how many individuals we have in the nth generation? We have psi n individuals. So the number of individuals in the next generation equals to the sum of these random variables eta, but the number of elements in this sum is random, you see? And all the entries of the sum are independent and identically distributed. So this is the main formula. So natural example where this works, example, is the following: if eta ni equal to 2 with probability p and to 0 with probability 1 minus p, for some p between 0 and 1, then we can think that this is the evolution of population of bacteria. Evolution of population of bacteria. Because look, what bacteria can do? Bacteria can die, or if it lives, then it divides divides two bacteria. Okay, so this is exactly the situation. So with probability P, it divides, it becomes 2 bacteria, and with probability 1 minus P, it dies. Okay, and then we ask the question, how many bacteria we will have after say 10 iteration of this procedure. Okay, so exercise problem, which I'll ask you to solve at home. So this will be in the list of problems which I'll put on the website of the course. Prove that this stochastic process forms a Markov chain. Forms a Markov chain. The proof is actually similar to the proof that the random walk forms the Markov chain. Which questions actually people ask for this model? So basically, you can ask different questions. You can ask with which probability, how many descendants will you have at the nth generation. But the most basic and possibly the most interesting question is as follows. So you asked with which probability everybody will die. So with which probability at a given moment of time you will not have. So the size of population will be equal to 0. And the main result concerning this model is the following theorem. I think that this is theorem number 15. Yes. So theorem 15. Theorem 15. Probability that there is n such that psi n equals to 0. So there is a generation at which will not give any descendant. So there is a generation of size 0. This probability equals 1 if the expectation of eta ni less or equal than 1. Let me write it more accurately. Less or equal than 1, and it is less than 1. It is less than 1 otherwise. If this expectation is strictly larger than 1. The only additional assumption that I need is that this eta I, they aren't equal to constant. So look, all eta I n, they are identically distributed, right? Then I can, all the expectations are the same. So in principle, it's possible that these random variables, they are not random, so that they just take constant value. This situation is, I mean, it's very boring. If this value is 0, then you will not have any descendants, right? Then everybody will die immediately. If this eta equals to 1, it means that everybody gives only exactly 1 descendant, and then the size of the population will be equal to the size of the initial population, right? And if it is larger than 1, then you will have exponential growth of the population, right? So this situation is not interesting. If eta is not constant, then we have very actually natural result. If the average number of descendants is strictly larger than 1, then probability that a given moment of time, that there exists moment of time such that everybody will die, is strictly less than 1. Of course, this event may happen, right? This event may happen with positive probability, but this probability is strictly less than 1. But if the number of descendants less or equal than 1, the average number of descendants, then the probability that one day everybody will die equals to 1. The only surprising thing actually is that the probability that everybody will die equals to 1, even in the case when the expectation equals to 1. You see, if the number of descendants is just constantly equal to 1, just is not random and just equals to 1 for every omega, then you will have that the number of descendants in each generation coincides with the number of sorry, that the size of the generation of each generation will be equal to the initial size. But if this random variable is indeed random, it is not constant. It turns out that even in the case when the average number of descendants equals to 1, everybody will die with probability 1. Do you see? So let me maybe repeat this in Russian. Смотрите, значит, просто это по-моему, довольно немного удивительная история, поэтому я хочу повторить этот кусок на русском. Значит, смотрите, естественно, что когда среднее число потомков строго больше единицы, ну, тогда, конечно, вероятность того, что в какой-то день, значит, все поколение вымрет, вся популяция вымрет, но вероятность этого события меньше единицы. В ситуации, если число потомков равно константе, тогда, и эта константа равна единице, тогда, конечно, вы имеете вот это соотношение, да? Но при этом размер каждого следующего поколения будет естественным образом совпадать с размером исходной популяции. Так? А вот если число потомков случайная величина и не равна константе, не равна единице тождественно, но при этом в среднем число потомков равно единице, то оказывается, что все равно с вероятностью 1, с вероятностью единицы, значит, все вымрут рано или поздно. Вот. Ну, а если меньше единиц, то, ну, само собой, с вероятностью единицы все вымрут. Okay, do you have any questions concerning the statement of the theorem?
Да, вот есть один вопрос.
Да.
У нас для всех n и для всех i мат ожидания меньше либо равно 1 в теореме.
Ну, потому что от n и от t эта история не зависит, потому что они одинаково распределены. Я попросил, чтобы смотрите, чтобы все это были IID, Independent Identically Distributed, значит, независимые, одинаково распределенные. Видите? Ну, а если у вас случайные величины одинаково распределены, то у них мат ожидания совпадают. Поэтому я вот здесь, если хотите, могу написать не это NI, а это, значит, там 0, 0, 0, 1. Да? Будет то же самое. Так, понятен ответ?
Да.
Да? Отлично. Okay, so more questions? If no, let us prove the theorem. So actually this proof is, I think that this is the first non-trivial proof in my course. So first let us note the following thing. Let me write the probability I am interested in the following form. I use the law of total probability, формулу полной вероятности. I take the summation over all natural numbers I. And I write the following formula. I take conditioning at the event that at generation 0, I have exactly I descendants, then I should multiply it by the probability that in the initial generation I have exactly I individuals. So look, since my omega, my space of elementary, my state space or space of elementary events, it consists, it can be represented as this joint union of the events that psi 0, which is random, equals to I, then this formula is true, right? Because of the law of total probability. Law of total probability. But then let us look what is this. This probability describes the situation, describes the same question, but for a different Markov chain. This probability corresponds to the Markov chain where at the initial moment of time I have deterministic number of deterministic size of the population. So I have exactly I individuals, right? Let me write it down. This is a probability of extinction. This is вымирание. Вероятность вымирания. Probability of extinction of a population which starts from size I. Then if my probability I'm interested in, so let me introduce notation. Let me call this guy epsilon, because I'll write this probability too often. To simplify the life, I will call it just epsilon. Then epsilon equals to 1. So actually, in my theorem, I ask question if epsilon equals to 1 or it is strictly less than 1, right? So according to this formula, epsilon equals to 1 if and only if each probability of extinction for every I equals to 1, right? Because if any of these probabilities is less than okay, this isn't very good logic, right? Because you may have situations that this guy equals to 0, then if one of these probabilities is less than 1, then it's okay. Okay, so sorry, let me use slightly different logic. Let me first just look at these probabilities, and then note the following. So the probability that everybody one day will die, conditioning at the event that at the initial moment of time you have exactly the number of your population, the size of your population is I, it equals to 1 if and only if the probability the following probability equals to 1. Look, I replace the condition that I have individuals in the zeroth generation, but by the condition that I have one individual at 0 generation. Why is it true? Just because, look, just because if this is true, then if this probability equals to 1, then this probability also equals to 1, because the processes that started, look, because individuals, they do not interact with each other, right? So if the probability that the population to which this individual gave birth will disappear one day, if this probability equals to 1, then the probability for this for descendants for the population which is obtained by this guy, the probability that it will disappear also equals to 1, and for this guy also, and for this guy also, right? So it means that the probability that everybody will die also equals to 1. And the other way around, you can argue similarly, right? If this probability equals to 1, then for everybody, for every individual at the 0th generation, the population to which it gives birth should disappear one day. Okay, so this is true. So let me repeat this passage in Russian, because I'm sure that it explained very good. Смотрите, значит, давайте я повторю. Вот что я здесь написал? Я здесь написал, что вероятность того, что у меня в начальный момент, значит, я рассматриваю ситуацию, когда у меня фактически в начальный момент времени только один индивидуум, так? Значит, и я рассматриваю ситуацию, когда вот та ветка, та популяция, которую он породил, что эта популяция однажды вымрет. И я, значит, интересуюсь ситуацией, когда это вероятность этого события равна единице. Значит, ну смотрите, но вот здесь вот я интересуюсь аналогичной ситуацией, но только в случае, когда в начальный момент у меня не один индивидуум, а когда у меня ровно и индивидуумов, значит, и это детерминистское число, это не случайная величина, значит, просто число. Вот, ну смотрите, если тот, кто дает, значит, если популяция из-под одного индивидуума вымирает, то в этом случае, значит, популяция вот здесь просто из-под каждого индивидуума вымрет с вероятностью единицы, так? Потому что индивидуумы между собой никак не взаимодействуют. Вот, поэтому, значит, если вот эта вероятность равна единице, значит, эта вероятность равна единице. Ну и обратно это тоже работает. Если вот это все вымерло, то, значит, популяция, из которой вышла из-под каждого вся вымирает с вероятностью единицы, значит, и это вымирает. Вот, поэтому, so this means that, look, if epsilon equals to 1, so if epsilon equals to 1, then at least one of these probabilities should be equal to 1, right? Otherwise, it's impossible. Because the sum of probabilities should be, the sum of these probabilities should be equal to 1. Then we get that. Let me write it below. Then we get that the probability of extinction starting from one individual equals to 1. And the other way around, look, if this probability equals to 1, then all these probabilities equal to 1, and it means that, look, here you take a sum of 1 multiplied by the probability, and the sum of these probabilities should be equal to 1 because of this. So epsilon equals to 1. So it means that we have equivalence. We have the equivalence. What is the corollary? Corollary is that it suffices to prove the theorem for the case when psi 0 equals to 1. Okay, is it clear?
Yes.
Perfect.
Yes.
I will call this part step 1. So I'll divide my proof in several steps. This will be step 1. Then step 2. So from now on, we assume that at the initial moment of time we have only one individual according to the first step. So let me recall you the following definition. I think that most of you are familiar with this definition. This is definition of generating functions, производящие функции. So the proof will be based on generating functions. Generating. So let me write it maybe slightly in slightly briefer. So let x. Well, x is not very good because usually this is a state space. What we have else. Okay, alpha be a random variable. And let us assume that alpha takes natural values. Okay. Then the following function, I will denote it phi alpha of z, which is the expectation of z taken to the power alpha. Z here is a complex number, which is in absolute value smaller than or equal to 1. And this function is called generating function. It's called generating function. For the random variable alpha. In particular, if for z you take a point of unit circle on the complex plane, then you'll get the function some, let me call it psi of t. This is expectation e to the power I t alpha. And what is this? This is just characteristic function. Characteristic function of the random variable alpha. So this is for those who have already taken the course of probability, because these people, they know that characteristic function plays central role in results like central limit theorem and so on. And moreover, the characteristic function uniquely determines the distribution of the random variable alpha. So generating function is a good object. But it also uniquely determines the distribution of the random variable. But I will not need this property of generating function. I will use it in a slightly different manner. Yeah, what exactly do I mean by this expectation? I mean, by definition, I have just written the following thing. I have just written sum from k equal to 0 to infinity z to the power k probability that alpha equals to k. I have written the definition of the expectation, right? Because my random variable takes natural numbers. But here there is a singularity because when z equals to 0 and k equals to 0, I get 0 to the power 0. It isn't clear what is this. By definition, I put it equal to 1. Okay. Then, with such definition, exercise, we have the following properties of the generating function. Phi alpha is continuous without this definition, it wouldn't be continuous at 0. Continuous convex function. Okay. So in particular, let me note that it is well defined, and since and moreover it is bounded just by 1, because it is less or equal than absolute value of z to the power alpha, and this is less than or equal to 1 because z is less than or equal to 1. Okay. Nice. Do you have any question concerning the generating functions? So let us denote by phi n of z the generating function of my random variable psi n, which is I recall that this is a size of the generation at the moment of time n. Then look, then what is phi n of 0? Phi n of 0, this is exactly the probability that psi n equals to 0, because in this series, when z equals to 0, only the first term may be non-zero, right? Because I'll have for the first term when k equals to 0 and then z equals to 0, I'll have 0 to the power 0, and I set it to be equal to 1, while the other terms, they will be killed by 0 to the power, to some positive power, which is 0. Let us consider. Okay, let me also note the following thing. I can rewrite this probability as the probability that psi m equals to 0 for any m more than or equal to n. Because if at moment of time n, I do not have the size of generation is 0, then the size of the next generations will be also equal to 0. Perfect. Let us consider the limit of phi n of 0 when n goes to infinity. When n goes to infinity. This is the limit. N goes to infinity of these probabilities. That from some moment of time there is no anybody, and I claim that this equals to the probability that there exists n such that psi n equals to 0. And this probability, this is exactly the probability we are interested in. This is exactly our epsilon by definition. Who understands why is this true? Look, just this is called the continuity of probability. So if you have already taken the course of probability, then you should know it. Otherwise, let me explain. Let me explain now. So let us consider a sequence of events where each previous event is contained in the next event. Значит, предыдущие события вложены в следующие, так? Я сейчас объясняю вот этот вот переход. So we have such picture. This is AK plus 2. This is AK plus 1, and so on. Then the probability that of the event AK, it tends, when K goes to infinity, to the probability of the event A, where the event A is given as a union of all events AK from 1 to infinity. Look, actually, what I have told the following: that let's assume that we have such picture, and then you have some event A, which is obtained by taking union of all these expanding events, right? Then the probability of this event AK, it tends, when K goes to infinity, to the probability of this union. This is called continuity of probability. Continuity of probability. Actually, continuity of probability, this is just it can be taken as an axiom when you construct the probability theory, but usually people do not take this as an axiom, but they deduce it from sigma additivity of probability. Basically sigma additivity of probability is just, I think this is just equivalent to the continuity of probability, or it is almost equivalent. Okay. Значит, я повторю на русском. Смотрите, это называется непрерывность вероятности. Это может быть, вот эта история может быть принята как аксиома теории вероятности, но обычно ее не принимают за аксиому. Обычно говорят, что вероятность сигма аддитивна, и это аксиома вероятности. Ну, а дальше непрерывность вероятности выводит оттуда, но это, в общем, сигма аддитивность вероятности и непрерывность — это то ли совсем эквивалентные вещи, то ли почти эквивалентные. Значит, да, и сейчас небольшое отступление для, так сказать, второкурсников и там для третьекурсников. В общем, для тех, кто ходил на ликбез по теории вероятности в начале курса, что смотрите, у нас ничего такого с вами не было, потому что мы рассматривали не более чем счетное множество элементарных событий. Так? Но вот здесь вот эта история, она существенна, когда у нас континуальное вероятностное пространство, то есть континуальное число возможных элементарных событий. Тогда появляются всякие вещи сигма аддитивности и прочие штуки. И вот в частности вот такая история появляется. Смотрите, когда мы хотим рассматривать вот такой вот предел, когда мы хотим устремлять n к бесконечности, то есть время к бесконечности в нашей марковской цепи, нам уже не обойтись на самом деле вероятностным пространством с не более чем счетным числом элементарных событий. Ну, потому что просто число последовательностей, состоящее из ноликов и единичек, оно уже континуально. Да? Вот, поэтому даже для марковской цепи, у которой всего два состояния, значит, множество элементарных событий, если вы хотите рассматривать цепь на бесконечном времени, то оно уже вынуждено быть континуальным. Ну и вот появляются вот такие эффекты. Okay, so let us note that in our problem for AM, we can take the event that psi m equals to 0 for any m more than or equal to n, but this is not am, this will be an, right? And indeed, you see that these events, the previous is included to the next one. Oh, it is not included. Let us think. Wait. Or the other way.
an
Could you
plus 1 is included to an.
an plus 1, the other way around, right? An plus 1 is included to an, right? Because
Yes.
if everybody is dead from starting from n plus 1, then if everybody is dead starting from n, then everybody is dead starting from n plus 1. Okay, but not the other way around, because if everybody is dead starting from n plus 1, it doesn't say anything about an. This is true. Okay, very nice. Then I'll just slightly change my picture, because the continuity of probability, it also works in the different direction. Непрерывность вероятности также работает в другом направлении. Значит, просто вот здесь вот нужно взять тогда не объединение, а пересечение. Это, в общем, одно и то же. Это через дополнение одно в другое перекручивается. Вот. Ну и, соответственно, здесь тогда на моей картинке, значит, вот это вот А, это самое внутреннее множество. Ну а дальше понятно, что это там А, К, плюс 1, а вот это вот АК. Okay, yes, sorry. Perfect. So that's why actually we have the equality, because the intersection of all AK, this is exactly the event that there exists moment of time n when psi n equals to 0, when everybody is dead. So now finally we have the formula that that says that we can compute the probability which we're interested in just as a limit of our generating functions taken at the point 0. Taken at the point 0. Step 3. Step 3. So let us try to compute this generating function phi n. Generating function phi n. So I recall you that psi 0 equals to 1. Then phi 0 of z, this is the expectation of z to the power psi 0. This is just z. Okay. What is phi 1? This is the expectation of z to the power psi 1, and this is the expectation of z. What is psi 1? If psi 0 was 1, this is eta 0 1. But what is this? What is this? This is exactly the generating function. The generating function for the variable eta 0 1. Of course, all these generating functions for all eta, they are the same, because the random variables eta are independent and identically distributed. And let me denote them by psi. Okay, by psi. So we have phi 0 equal to z, phi 1 equals to psi, and I have the following lemma. It's lemma 16. Psi n of z equals to the composition of the function psi n times. So let me maybe, okay, let me keep it as it is. Okay, no, let me maybe write it as psi composition power n. Okay, this is just the notation. Let us prove it. So actually we already have the base of induction because phi 1 equals to psi. Now we need to prove step of induction. We assume that this holds for n, and let us prove it for n plus 1. So phi n plus 1 of z is plus phi n plus 1 of z. This is the expectation of z to the power psi n plus 1. Psi n plus 1, I recall that this is a number of the size of population at the moment of time n plus 1. And what is actually psi n plus 1? This is the sum eta n1 plus etc. plus eta eta n psi n. So I sum up numbers of descendants for every individual from the previous generation. Look, this is just okay. So what is the problem here? The problem here, let me write it maybe in the following way. Oh. So actually, this is a product of a number of very similar objects, because I recall that all eta and j is identically distributed, but the problem is the number of terms in this product is random, right? Смотрите, значит, это произведение независимых, это произведение очень похожих объектов, потому что все это n-житы, они одинаково распределены, но проблема в том, что число сомножителей случайно. Если бы число сомножителей не было бы случайно, то так как вот эти штуки независимы, я мог бы написать просто, что это равно произведению мотожданий, потому что мотождание произведения равно произведению мотожданий для независимых случайных величин. Так? Но здесь так написать не могу, потому что здесь еще вот это вот ксиен вмешивается, потому что это случайная штука. Поэтому нужно с этим что-то делать. И вот здесь есть такой стандартный прием. So now I'll use the standard method to resolve this problem that the number of terms in this product is random. I will note that my set of elementary events can be represented as disjoint union, or all I from 0 to infinity of the events that psi n equals to I, right? Because psi n takes some value, then we have this equality. But then it means that one, just number 1, it can be represented as the following series, as a sum from I equal to, maybe I'll write k instead of I, from k equal to 0 to infinity indicator function of the event that psi n equals to k. of omega. What is this indicator function? Just by definition, this is a random variable which equals to 1 if eta n of omega equals to k, and which equals to 0 otherwise. So are you agree with this?
Yes.
Yes.
And then I will just insert this one into the brackets here. Then I will obtain the following story. I will obtain the summation from k equal 0 to infinity, the expectation. I have the product as above. And then I have the indicator function of the event that psi n equals to k. Very nice. Oh, this was k. Okay. Then look, if psi n is different from k, for those omega for which psi n is different from k, I have that this indicator equals to 0. So this term is non-zero, can be non-zero only for those omega for which we have psi n equals to k. Then it means that this psi n for non-zero terms always equals to k. So I can just replace it here. I can just replace here by k. And I'll do this. Z eta n1, Z eta nk. And also I have the indicator function. Then look, eta nj and psi n are independent. Are independent because I recall that you obtain psi n plus psi n you obtain from eta n minus 1. From eta n minus 1. That's why these guys are independent. And then we use that the expectation of product of independent random variables equals to the product of expectations. Because now the number of terms in the product is deterministic. So we have got rid from this problem with the random number of terms in this product, and now it is deterministic. Look, so we have this expectation. All these expectations, such expectations are equal because eta and j are identically distributed. And also I should multiply by the expectation of the indicator function. Of the indicator function. I have some problems with the letter k, I don't know why. Perfect. What is this? This guy, this is just the generating function of the random variable eta n1. So in my notation, this is I recall this is the function psi, right? This is the function psi. But what is the Sorry. Yeah. What is actually the expectation of the indicator function? Can you say?
It's probability of psi n equals to k.
Yeah, exactly. Because look, this guy equals to one when psi n equals to k, and to 0 otherwise. Then I should multiply 1 by the probability of this event, and I get exactly probability that psi n equals to k. That's why I insert here this probability. And now who can say what is written here? What is this? Actually, what is this?
Expectation of psi z
Yes,
to the power of psi n.
yes, exactly. Look, because this is just the definition of this expectation, right? But this expectation, what is this? What is this actually? This is the generating function of the random variable psi n taken at the point psi, right? So this is phi of psi of z. So look, in conclusion,
It's phi n.
thank you, yeah, phi n, thank you, phi n. In conclusion, we have started from here. We have got that phi n plus 1 equals to phi n of psi, right? And then by induction, it means that psi n plus 1 equals to just psi, composition with psi, composition with etc., composition with psi n plus 1 times. Okay, so this is exactly what we wanted to prove. Very nice.
So,
Yeah.
and I think that in the previous lemma, the initial writing about inclusions was correct, because the sign of
Okay.
existence corresponds to the union, and the sign for all corresponds to intersection.
Well, yes, but here,
If we are dead at the point of time n, then we are dead at the point of time n plus 1. Therefore, an is contained in an plus 1, but not
an
the other
plus
way.
1, but I think that no, wait, if we are dead, okay, so давайте на русском. So let us speak about this. Maybe in Russian it will be just slightly simpler. Значит, смотрите, значит, если у нас, если все померли в момент времени 2, так, в момент времени 2, то
То уж
значит,
тем более в третьем моменте тоже.
в третьем моменте тоже все померли. Это значит,
Может, нарисуем это, круги вот.
Это, ну вот, смотрите, давайте, значит, вот это, значит, момент времени 2. Это вот событие, что все померли к моменту времени 2. Значит, к моменту времени 3 все тоже точно померли, так? Все тоже точно померли. Значит, но вот если к моменту времени 3 все померли, это не значит, что к моменту времени 2 все померли. То тогда третий вот здесь, да?
Да. Ну, это как раз то, что я говорю.
Так, действительно, ну, я честно скажу, в этом всегда путаюсь, что в какую сторону. Значит, если к моменту времени 3 все померли, к моменту времени 3 все померли, значит, к моменту времени 2 ничего не можем сказать.
Еще не факт, да.
Yes.
Вот с квантерами это легче запомнить. Вот существует это объединение.
Да, то есть мы можем быть вот здесь. А если к моменту времени 2, значит, мы померли, то к моменту времени 3 мы тоже надежно померли, поэтому мы точно в 3. Okay, yeah, so I agree with Camille. Yes, I'm sorry. So this was the like this, the initial version was correct. The initial version was correct. Uh-huh. Yeah. Perfect. Okay, so now we have, look, we have very nice result. We know that the probability we're interested in, this is just such limit of generating functions when n goes to infinity at 0. And then we know explicit formulas for the nth generation function. So it turns out to compute this limit. And this, I will call it step 4. Step 4. So I recall that epsilon equals to limit when n goes to infinity of psi taken at like composition n times at 0, but then I will write it also in the following. Okay, so let me then do the following thing. I will compute psi of epsilon. Psi of epsilon, this is psi of this limit, right? But the function psi is continuous. Then I can exchange it with the limit. What I'm doing, I get n plus 1 here. This is actually the standard trick, so I suggested you to take it into account. But what is this? This is of course the same thing that here. So this is epsilon. Since psi is continuous. Since psi is continuous. Very nice. It means that our probability of extinction, probability that at some moment of time everybody is dead, this is exactly the fixed point of the function psi, right? So now it remains to understand how fixed points of the function psi may behave. Let us try to draw a picture of the function psi. X, psi of x, psi of x. So here we have x equal to 1. Of course, epsilon is smaller than or equal to 1 because epsilon is a probability, and it starts from 0. So I'm interested in this interval. In this interval. Look, let me draw the diagonal, and let me try to understand what is the value of psi at the initial moment of time. So psi of 0, what is this? Since this is a generating function, this is a probability that eta nj equals to 0. And this probability, of course, it should be less than 1, because if this probability equals to 1, then I mean, we do not have a subject to discuss. It means that this probability 1, you do not have descendants, right? So it means that you die at the first generation. Значит, мы не рассматриваем ситуацию, когда эта вероятность равна единице, потому что это что значит, что эта вероятность равна единице? Это значит, что просто с вероятностью 1 у вас нет потомков вообще, ни у кого. Это значит, что в первом же поколении все помрут. Тут говорить не о чем. So we assume that this is smaller than 1. And here is it, psi of 0. What is psi of 1? Psi of 1, this is expectation of 1 to the power eta nj. This is, of course, 1. So psi of 1 is here. And we are interested in fixed points of the function psi. So these are the intersections with the diagonal. Значит, нам интересна фиксированная точка, то есть пересечение с диагональю, неподвижная точка. So to understand where this point can be situated, let us compute also the derivative of psi over its argument at the point z equal to 1. So the derivative at this point. By the definition of the generating function, this is the sum from k equal to 0 to infinity, k times z to the power k minus 1, the probability that eta n I equals to k. Then I substitute z equal to 1. Here I obtain the summation, the same summation, but without z. And what is this? This is exactly the expectation of eta. Let me call it mu. Let us first assume that mu is less than or equal to 1. This is A. Then what do we have? We have that the derivative of our function at this point is less or equal less than or equal to 1. So it means that I mean, look, it cannot go like this, right? It cannot go like this. This cannot happen. So it means that it goes here like this, right? Or maybe like this. Okay. Значит, смотрите, собственно, поведение функции, вот как я сейчас нарисую красным, оно невозможно, потому что производная не меньше единицы. Так, вот здесь, значит, производная больше единицы получается, потому что она значит, ниже диагонали. Ну, соответственно, она должна быть выше диагонали, чтобы, ну, вот в окрестности точки единицы она должна быть выше диагонали, чтобы производная была, значит, меньше либо равна единице. But what does it mean? It means that the function may behave only like that. Okay, so the picture is not too good. So it means that it should behave somehow like that. Because the function is convex. You see, the function is convex. So it's forbidden for the convex function to make something like that. It's forbidden. Смотрите, функция выпуклая, поэтому она не может вот так вот сделать. Она не может, значит, несколько раз диагональ пересечь. Что она, собственно, у нее есть базово два варианта. Она может либо вот так пройти, хопа, либо сразу прийти вот в эту точку, потому что она выпуклая. Значит, а вот вариант, который я нарисовал вот здесь, невозможно, потому что производная меньше либо равна единице. Значит, поэтому остается вариант, который я вот сверху нарисовал. Сейчас все остальное, кроме него, сотру. Okay, so finally we have the only possibility is that the function behaves like that, since it is also convex. I recall that I have given an exercise which claims that the generating function is convex. But what does it mean? It means that epsilon equals to 1, the unique fixed point of the function psi on the interval 0, 1. Since epsilon, it must be the fixed point of the function psi, then epsilon equals to 1. Значит, epsilon это обязан быть фиксирован неподвижной точкой функции psi, поэтому он обязан быть равен единице, деваться больше некуда. Видите, как получается, да? So here I just argued looking at the picture, and I leave rigorous argument for you as an exercise, because I mean everyone among you can do this by yourself. This is some simple analysis of the first year education. So it remains to consider the situation B when mu is more than or equal to 1, and then I leave it also as a problem, which will be in the list of problems. Actually, the argument is similar to what I have just used, but slightly more involved. I think that you will need to find one more small idea, one more argument to deal with this situation. You see here the problem is that actually you will have two fixed points. One fixed point is always z equal to 1 because of this. But in this situation you will have to show that there is also another one fixed point which is situated somewhere here. Hop. So let me call it y. And then you will have to show that. So then you will have to choose between the two possibilities: epsilon equals to y or epsilon equals to 1. But the point is that this is impossible. So you will need to find an idea why epsilon in fact equals to y, not to 1. Okay? Так, коллеги, есть ли вопросы какие-то по этому делу?
Yes, I have a question. Why the limit with epsilon equals limit of psi composed n times? Why does this limit exist?
Why does this limit exist? Okay. Just a second. This is this is a good question, but so if we need just a second. Okay. Just it exists. It exists because this probability is well defined. This limit exists because this probability is a well-defined probability. Because of continuity of probability. Because this event exists, right? This event exists. Then this event, it must be this limit.
Yes. Okay. Thank you.
That's it. So more questions? No questions. Then we should finish for today. The next time we'll have offline lecture. The time after the lecture after the next one will be also offline. I think that we will not have control work in 2 weeks, but I will think more about this. And then it will become again online, unfortunately. Okay, so see you the next time.
Okay. Thank you, Professor. Bye-bye.
Goodbye.
Bye.